So I'll start with outline done in nice pictures. So the context in which the talk is placed is essentially a top-down approach complementary to the more popular swampland program, since we start from actual top-down string models breaking supersymmetry at high energies instead of trying to constrain low energy effective field theories. So we try to learn whether these theories have some consistency conditions directly within the UV framework, so to speak. In order to do this, we studied instabilities of ADS vacua, and they come in both perturbative and non-perturbative flavors, as I will explain later. And hopefully, the very fact that these are ADS vacua can allow us to go somehow beyond the low energy effective field theory regime using some ideas based on holography and brane dynamics, as I will explain later. So let me first begin presenting the actual non-supersymmetric string theories that we work with, and then I will go on to show the ADS vacua we found. So these are three 10-dimensional non-tachyonic string models. And the first is a heterotic model, which is perhaps the simplest to describe. It's a non-supersymmetric projection of the E8 times E8 heterotic superstring, and it has a residual gauge group of SO16 squared. And breaking supersymmetry via this projection induces a one-loop vacuum energy, which is non-zero. And this feeds back into the low energy effective action as an exponential potential for the dilaton that looks like this. So already we can see some low energy consequences of SUSY breaking. And then there are two orientifold models, which arise as, so the first one is an orientifold of the type 0b string, which is non-supersymmetric and tachyonic, whereas this type 0 prime orientifold removes the tachyon and leaves a U32 gauge group. And then the last one is an orientifold of type 2b string theory, which leaves a USP32 gauge group, and it's somehow a cousin of the more well-known type 1 superstring. And the key difference here is that from a space-time perspective, one is adding anti-D9 branes together with the O9 plane instead of regular D9 branes. And this makes all the difference, since the total tension of these objects does not cancel out anymore, hence inducing this exponential potential for dilaton again, albeit from a different source. And this configuration breaks supersymmetry on these open sector, hence the term brane supersymmetry breaking. But from our point of view, we are interested in these ADS solutions, which are essentially the only family of controlled solutions that were found, compared to the various solutions that were found back in around 2000, which feature large corrections somewhere in their space-time. So let me move on to explain what these ADS solutions look like. So the low energy description of these theories looks like this, and it's pretty much your ordinary run-of-the-mill low energy effective field theory, except again for this exponential potential for the dilaton, which is a key feature of this type of supersymmetry breaking. But nevertheless, turning on fluxes, which we can do thanks to the presence of this free-form field strength, we can tame this imbalance between alpha prime orders and actually build up a controlled solution. And these solutions have the Freund-Ruben structure of a flux compactification with ADS and a compact Einstein manifold. Here we took we took the sphere for simplicity. And depending on the model, only one of the two types of fluxes can lead to a solution, either an electric flux or a magnetic flux. So there's no duality in this sense. But computationally speaking, the most useful feature of these solutions is that large fluxes lead to perturbative behavior. So small string coupling and small curvature. This is what allows us to perhaps expect that these solutions can be reliable. So
this is the solution of the minimum of something, or is it just the possible symmetries of the theory?
Well, if
a dynamical solution, or is just a possible solution?
It is a dynamical solution. If you will, it's a minimum of some sort of effective potential that arises from the combination of this red V potential and the flux contribution.
Okay, thank you.
So here are the actual values, or at least the relevant parameters. So in the orientifold models, the flux must be electric. And what happens is that working through the equations of motion as usual, one finds the curvature radii of ADS and the internal space, which scale like a positive power of n. Whereas the string coupling scales like a negative power of n, and so both alpha prime and GS corrections are suppressed. And most notably, in contrast to the supersymmetric case, which is essentially the ADS 5 times S5 solution, the string coupling is not a modulus anymore. And it is instead completely fixed. So the only parameter of this solution is n, which is essentially a flux numbering and is expected to be discrete. And moreover, as you can see, the solution is not scale separated. And then going on to the heterotic case, it's pretty much more of the same, except for the fact that the flux is magnetic. So the key point is that these signs are what they are supposed to be, and everything else is just algebra essentially. So these solutions appear to be reliable, and what we can do with them is study instabilities, right? So starting from perturbative instabilities, they are pretty technically involved, but conceptually the physics lies in the fact that the ADS curvature contributes to the effective mass of perturbative modes, so that they don't have to be just of non-negative square masses in order to be stable, as in flat space. Instead, the bound is a little bit relaxed. And this is what happens in the case of a free scalar. This is the celebrated Breitelloner-Friedman bound. But the more general bounds can be derived for different kinds of fields, different representations with mixings and the like. So given this conceptual point, what we did was study perturbations of these ADS vacua, and also other solutions that are these solutions with large corrections that I told you about briefly. So since we have an internal sphere, there are angular momenta going on for Kaluza-Klein modes, and it turns out that there's only a very small number of angular momentum values for unstable scalar modes. Right? So only scalar modes are unstable, and only for these small range of angular momenta, which means that ideally one should be able to remove them, either choosing a different internal manifold with different spectrum, or performing a suitable orbifold projection. In the heterotic case, this is easy to do, since an antipodal Z2 projection removes the odd angular momenta, introducing no twisted states. In the orientifold case, things appear to be more complicated than that. An additional interesting result that we obtained is that these other vacua, even though they feature large corrections somewhere, appear to be perturbatively stable, except for an interesting isotrope instability of this 10-dimensional cosmology, where the homogeneous tensor mode is unstable, thus hinting to a tendency towards spontaneous compactification. So somehow breaking supersymmetry always leads to some dynamics of some sort, which is... Yeah, sorry, go ahead.
You say that there are unstable modes, but can you follow what happens when you switch the norm to which vacuum you flow?
Right. So this we didn't do yet. We didn't. I mean, I suspect that it's a pretty complicated issue. What we did do is to follow the process for non-perturbative instabilities instead, which is much easier to do since what happens is that the flux number changes. So in this case, we only identified the presence of instabilities, right? In the case of non-perturbative instabilities, we can actually follow along the process. Does that answer the question?
Yes.
All right, so talking about non-perturbative instabilities, this is what and again, in the framework of low energy effective field theory, one may be able to study those using instanton calculus, but conceptually the issue is quite subtle since these processes move you along this landscape of vacua for which we have no global knowledge. And in the supersymmetric case, it's not necessary to have it since any given supersymmetric vacuum is guaranteed to be globally stable. In this case, we don't really know what happens toward the end of this process. We can follow along, as I was saying, but it's harder to understand what happens toward the end of it. Nevertheless, we are trying to use this stringy perspective that we have, this vantage point, in order to try and go beyond building some intuition for what happens. And in order to do this, we developed this brane picture of what happens for non-perturbative instabilities, which take the form of flux tunneling processes, essentially the higher dimensional analog of the Schwinger reproduction effect. Happens because the vacuum energy of these solutions depends on the flux number in such a way that smaller n leads to smaller vacuum energies. And this means that these vacua can have a spontaneous tendency to nucleate bubbles that carry away some of the flux, right? And smaller n means stronger coupling and higher curvature. So this is a problem, potentially. And this is why we tried to develop this brane picture. And the basic intuition is that these bubbles have exactly the right dimensions and charges to correspond to the actual fundamental branes of these theories, namely D1 branes or Navier-Schwarz 5 branes. So this is already a nice hint. And then there is the observation that, at least in the known cases, this type of flux ADS geometries generally correspond to near horizon geometries of some kind of extremal object. So in order to substantiate these ideas, first of all, we matched a gravity computation of the decay rate, which is essentially a Brown-Tate-Bohm / Coleman-de Luccia kind of calculation with instantons, with a more stringy brane instanton computation. And both actions, both decay rates take the form of an area minus volume term, which is typical for this kind of physics. And it turns out that after some algebra, the whole decay process hinges on this parameter beta that appears in this ugly function here, but that's not important. What's important is that for the decay to be consistent, this beta ought to be greater than 1, and most importantly, it must be of order 1 with respect to the flux. This is crucial because otherwise the decay rate will not be exponentially suppressed. And so this beta parameter relates the charge to tension ratio of these bubbles or branes to other factors. And it turns out that these consistency conditions impose precisely that the tension scales like GS to the correct power, so the power that fundamental branes in these theories have, namely D branes 1 over GS, Navier-Schwarz branes 1 over GS squared, and then more exotic branes have different scalings, but they all come from this consistency condition. So this is pretty promising, I would say. And what and then another interesting result is what happens after nucleation. So when nucleation occurs, these brane and interbrane pairs separate because they feel a potential, and this potential depends on this charge tension ratio, which in the string theories at stake ought to be 1, but nevertheless the potential for branes doesn't cancel out because of this V0 factor here. So this V0 appears just from the background, right? You do the computation, you find this number, and this number is crucially larger than 1, and it appears as a sort of enhancement, a renormalization of the bare charge tension ratio, which increases due to the interaction between these branes, which are supersymmetric by themselves, and the supersymmetric breaking ingredient in the background. So this is a very subtle manifestation of the weak gravity conjecture, if you will, and it's yet another encouraging hint. But then there's the other part of this whole picture, this whole brane framework, which is thinking of these ADS solutions as near horizon geometries of a brane stack. And in order to study whether this is the case, we looked at the most general geometry with those symmetries and fluxes. And what we found is that indeed one can recover an infinitely long ADS throat, characteristic of such extremal objects. But then once one goes far from the throat, instead of opening up to an asymptotic flat infinity, the space closes off at a finite distance with a curvature and coupling singularity. So even though we cannot trust what happens there, there is some strong coupling effect going on there, and crucially at a finite distance. So even though we cannot reproduce the usual ADM arguments to find tensions and charges for these branes from the asymptotic infinity, this geometry still has the same number of free parameters. So there ought to be some matching conditions between those, which we are working on. So all of this appears to be consistent, encouraging, but what can we do with all of this? And in order to go beyond effective field theory perspective and actually use these string intuitions that comes from these brane dynamics, the first plan would be to investigate these effects from the perspective of the world volume gauge theory that lives on these branes. And but this appears to be kind of hard for various reasons. First of all, a very simple computation of the holographic central charge for the ADS3 CFT2, let's call it that, case yields a central charge that scales with a fractional power of n, which means that whatever this theory is, it's probably strongly coupled. However, there is another interesting complementary direction to pursue due to the Uppsala group, which investigated it from a bottom-up perspective, which appears to be accessible from the low energy side, which is the fact that these expanding branes that nucleate host a de Sitter geometry with all the various features that you would expect in Feynman equations, Einstein equations more generally, the possibility to add matter and radiation in a string fashion. So this is also a very promising idea that gives in our concrete string models parametrically small cosmological constants. So this is actually kind of interesting. So let me conclude with a pretty diagram that summarizes what I told you about, namely ADS vacua in non-supersymmetric string theories and how we can use the instabilities to gain, hopefully, some understanding of what supersymmetry breaking really tells us. And it appears to us that the key take-home message here is that breaking supersymmetry, either through instabilities or through this appearance naturally of cosmological solutions, of inflationary type of solutions, it appears to be that SUSY breaking naturally leads to dynamics. It's hard to break supersymmetry and keep things still, much like in KKLT scenarios and like. So if this is true, it would be nice to kill two birds with one stone and actually break SUSY and get some dynamics out of it. So this is it, I'm done. Thanks for your attention.
Thanks a lot for the nice talk. Are there comments or questions?
Just a curiosity. This bubble of branes.
Yes.
This change of fluxes reminds me a little of some old stuff, which is
Are you talking about the Brown-Tate-Bomb construction?
No, the fact that the fact that you can have a theory which changes at the top of a conifold, you have a different the change of fluxes.
So this reminds me about these ideas of cascading RG flow.
Yes.
Is this what you're talking about?
Yes.
Right. Well, yeah, it does remind of that. And I mean, indeed, as I briefly mentioned in this diagram here, we do have an interpretation of these processes in terms of RG flows, much like they do in the work by, it was Klebanov and
Yes.
I guess Rassler, right? The Klebanov-Rassler solution. Yes. So we do have an interpretation in terms of RG flows, and we wrote it up in one of those three papers, the one with Alessandro Bombini. And I have some backup slides if you want to get deeper into detail. But, well, maybe I can try just to give you some flavor. Let's see. Yeah, this is it. So basically, we proposed an interpretation of these processes in terms of RG flows. Since these ADSs are never truly completely stable, the corresponding dual field theory cannot be an exact CFT. So at large n, it will be close to a CFT in some sense, though it's not clear how exactly. And there ought to be some relevant deformations that correspond to the possibility of nucleating the bubble. And then, so in order to actually check that this works out, we computed the entanglement entropy of the dual theory, and actually it goes down monotonically, as you would expect from an RG flow. So this interpretation is not completely solid, but it does appear to make sense.
Okay, thanks.
Other questions?